Chemistry is defined as the study of the composition, structure, and properties of matter, and the reactions by which one form of matter may be converted into another form. Chemistry is an active evolving science, and has vital importance to India and entire world. The subject has very ancient roots, but it is a modern science. The basic knowledge of chemistry is essential for development of subjects like physics, biology, geology, engineering, environmental science, and many other subjects. Therefore, chemistry is called as central science. In 21st century, the subject chemistry witnessed tremendous growth. During 20th century, the knowledge about chemistry has increased so much that the subject chemistry is divided in several branches as follows. Physical chemistry, the branch of chemistry that deals with the structure of matter, the energy changes, and the theories, laws, and principles that explain the transformation of matter from one form to another. In organic chemistry, this is the branch of chemistry that deals with chemistry of elements other than carbon, and of their compounds. Organic chemistry. This is the branch of chemistry that deals with the reaction of the compounds of carbon. Analytical chemistry. This is the branch of chemistry dealing with the separation, identification, and quantitative determination of the compositions of different substances. Biochemistry. This is the chemistry of the substance, consisting of living organisms. This is the chemistry of the substance, consisting of living organisms. Pharmaceutical, environmental, nuclear, are also some more branches of chemistry.
Classification: solids, liquids, and gases. Matter can be classified into three categories according to its physical state. These three categories are solids, liquids, and gases. 1. Solids. An object is said to be a solid if it has a definite shape and volume that cannot be changed easily. Some common examples of solids are chair, table, iron, common salt, sand, wood, etc. Solids have relatively high densities and are generally incompressible. 2. Liquids. An object is said to be a liquid if it has a definite volume but changes shape quite easily. A liquid flows to take the shape of the container. Some examples of liquids are water, milk, kerosene oil, gasoline, cooking oils, mercury, bromine, etc. Liquids also have high densities, but their densities are lower as compared to solids. Liquids are also almost incompressible. Solids and liquids are also known as condensed states of matter because of their well-defined volumes. 3. Gases. An object is said to be a gas if it has neither definite volume nor definite shape. A gas occupies whole of the space that is available to it. Thus, a gas acquires the volume and shape of its container. Gases have relatively low densities and are highly compressible. Some common examples of gases are air, steam, acetylene, methane, hydrogen, etc.
Pure substances versus mixtures. Pure substances have a definite chemical composition. They always have the same properties regardless of their origin. Mixtures have no definite chemical composition and hence no definite properties. Examples of pure substances: pure metal, distilled water, etc. Examples of mixtures: paint, mixture of oils, pigment, additive. Concrete, a mixture of sand, cement, water. Pure substances are further divided into elements and compounds. Elements are pure substances which cannot be broken down into simpler substances by ordinary chemical changes. Elements are further classified as metals, nonmetals, and metalloids.
Metals: gold, silver, iron, copper, aluminium, magnesium, calcium, sodium, platinum are a few metals. Metals have luster. The metals are hard. Wire or sheet can be made from metals. Metals are good conductors of heat and electricity. Metals lose their valence electrons to produce positively charged ions, that is, cations. Physical properties of metals. 1. Physical state. Under ordinary temperature, metals stay in solid state. However, metals like mercury and gallium are exception, which are in liquid state even at room temperature. Can you recall? You might have seen a doctor's pressure gauge to measure blood pressure during your visit to a dispensary accompanying your relative. Pressure gauge is an instrument used to measure blood pressure. In that, you might have seen a grey-colored liquid in a glass tube. What is that metal? The metal in a glass tube of a doctor's pressure gauge to measure blood pressure is mercury. 2. Luster. Take copper vessels at your home. Scrub them with lemon and rinse with water. Observe the luster before and after cleaning. Light gets reflected from the cleaned or freshly cut surface of metal and the metal looks lustrous. 3. Hardness. Generally, metals are hard, not soft. Exception: sodium and potassium are soft and can be easily cut by a knife. 4. Ductility. Have you ever gone to a goldsmith's shop? Have you seen the goldsmith making a wire of gold or silver? When a metal is pulled through a hole, its wire is formed. This property of metal is called ductility. 5. Malleability. Take an iron nail. Place it on a platform and keep on hammering it. After some time, you will see a thin sheet forming. This property is called malleability of metals. 6. Conduction of heat. Take a copper plate. Fix some wax at one of its ends. Heat the other end and observe what happens. Discuss with teacher. First, the wax melts. Second, this is because copper is a good conductor of heat. Third, when one end of copper rod is heated, the heat is transferred to the other end and hence the wax melts. Metals are good conductors of heat. Silver, copper and aluminium are the best conductors of heat. 7. Conduction of electricity. Which metals are used to make electrical wires? Metals are good conductors of electricity. Lead is an exception, which is neither a good conductor of heat nor a good conductor of electricity. 8. Density. Metals have high density. Sodium, potassium and lithium are exception, having lower density than water. The density of lithium is only 0.53 grams per cubic centimeter. 9. Melting point and boiling point. Generally, metals have high melting points and boiling points. Exceptions: Hg, Ga, Na, K. 10. Sonority. What is the metal that your school bell is made of? Metals used to make school bells are copper and tin. Note: bronze is an alloy of copper and tin and is used to make school bell. How does a school bell function? School bell is made up of metals. Metals are sonorous. Hence, school bell produces sound on striking. Physical properties of metals. 1. Physical state. Under ordinary temperature, metals stay in solid state. However, metals like mercury and gallium are exception, which are in liquid state even at room temperature. Can you recall? You might have seen a doctor's pressure gauge to measure blood pressure during your visit to a dispensary accompanying your relative. Pressure gauge is an instrument used to measure blood pressure. In that, you might have seen a grey-colored liquid in a glass tube. What is that metal? The metal in a glass tube of a doctor's pressure gauge to measure blood pressure is mercury. 2. Luster. Property of physical properties of metals. 1. Physical state. Under ordinary temperature, metals stay in solid. Physical properties of metals. 1. Physical state. Under ordinary temperature, metalloids. Some elements such as arsenic, As, silicon, Si, germanium, Ge, antimony, Sp, have properties which are intermediate between metals and nonmetals. Such elements are called metalloids. Compounds. Magnesium ribbon burns with a dazzling white flame to form a white ash. The white ash formed is magnesium oxide. It is an entirely new substance. Now, magnesium and oxygen are elements. They have combined to form magnesium oxide, which is a compound. Thus, a compound is a substance which forms when two or more elements combine in a fixed ratio by mass. The table here lists a few compounds and the elements that combine to form the compounds. Some compounds and their constituents. Elements sodium and chlorine combined form a compound, sodium chloride. When elements hydrogen and oxygen combine, they form water. Carbon and oxygen combine to form carbon dioxide, while sulfur and oxygen combine to form sulfur dioxide. Elements sodium and oxygen combine to form a compound to form carbon dioxide, while sulfur and sodium chloride. When elements hydrogen and oxygen combine, they form water. Carbon and oxygen combine to form carbon dioxide, while sulfur and oxygen combine to form sulfur dioxide. Elements sodium and oxygen combine to form a compound, sodium oxide. and elements silver and chlorine combine to form compound silver chloride. Properties of a compound. Let us now discuss the properties shown by a compound. A compound cannot be separated into its constituent elements by physical methods, but can be separated by chemical methods like electrolysis. This can be understood with the fact that water, which is a compound of two elements, hydrogen and oxygen, combined in a fixed ratio by mass, cannot be separated into hydrogen and oxygen by simple physical methods like sublimation, filtration, etc. But water can be broken down into its constituent elements, hydrogen and oxygen, by passing electric current through it. The properties of a compound are entirely different from the properties of its constituent elements. For example, the properties of hydrogen and oxygen are entirely different from the properties of water, which is formed by combining hydrogen and oxygen. Oxygen gas supports burning, hydrogen gas can burn, and water, which is formed by their combination, neither burns nor supports burning. In fact, water is used to extinguish fire. Isn't that amazing? A compound is formed when constituent elements combine in fixed ratio by mass. To form one molecule of water, the two elements, hydrogen and oxygen, combine in the ratio 1:8 by mass. A compound is formed when two or more elements combine with each other chemically. We cannot get carbon dioxide gas by simply mixing carbon and oxygen. They chemically combine to form carbon dioxide gas. Do you remember the activity in which you burnt magnesium ribbon in the presence of air? Magnesium and oxygen combine chemically to form magnesium oxide, which is a compound. Magnesium plus oxygen, which is present in the air, burn to give magnesium oxide. Energy is either absorbed or released when a compound is formed. When we burn coal, a lot of heat is produced along with the formation of carbon dioxide, which is a compound. We can write this as coal plus oxygen from air burn to give carbon dioxide gas plus heat. What is a mixture? Mixtures are constituted by more than one kind of pure form of matter known as a substance. A substance cannot be separated into any other kinds of matter by any physical process. We know that dissolved sodium chloride can be separated from water by the physical process of evaporation. However, sodium chloride is itself a substance and cannot be separated by physical process into its chemical constituents. Types of mixtures. Depending upon the nature of components that form a mixture, we can have different types of mixtures, namely homogeneous mixture and heterogeneous mixture. A homogeneous mixture is defined as the mixture which has uniform composition throughout its mass. For example, air, sugar solution, salt solution, alloys, soft drinks. A heterogeneous mixture is defined as the mixture that do not have uniform composition throughout their mass. For example, soil, rocks, etc. What is a solution? Now, if this was English, we would say solution is the answer to a problem, but this is science, so a solution is a homogeneous mixture of two or more substances. Lemonade, soda water, etc. are all examples of solutions. Usually we think of a solution as a liquid that contains either a solid, liquid, or a gas dissolved in it. But we can also have solid solutions, for example alloys, and gaseous solutions like air. Alloys is a solid solutions of two or more metals or a metal and a non-metal and cannot be separated into their components by physical methods. A solution has a solvent and a solute as its components. The component of the solution that dissolves the other component in it, usually the component present in larger amount, is called the solvent. The component of the solution that is dissolved in the solvent, usually present in lesser quantity, is called the solute. Some examples: aerated drinks like soda water, etc. are gas in liquid solutions. These contain carbon dioxide gas as solute and water, which is liquid, as solvent. Air is a mixture of gas in gas. Air is a homogeneous mixture of a number of gases. Its two main constituents are oxygen, which is about 21%, and nitrogen, around 78%. The other gases are present in very small quantities. What is a suspension? Now, non-homogeneous systems like those in which solids are dispersed in liquids are called suspensions. A suspension is a heterogeneous mixture in which the solute particles do not dissolve but remain suspended throughout the bulk of the medium. Particles of a suspension are visible to the naked eye.
liquid, and gaseous. The three states of matter. Matter exists in three states: solid, liquid, and gaseous. In solids, the constituent particles are held very close to each other, in some definite orderly manner. Hence all solids have some definite shape. The solids may be amorphous or crystalline. In case of crystalline solids, it may have simple cubical, body-centered cubical, or face-centered cubical, or hexagonal structure. Phosphorus exist as P4, a trigonal structure. Sulfur exist as S8, a crown-shaped structure. Carbon graphite has planar layer structure. Hence it is soft. Carbon diamond has three-dimensional network structure, and it is very hard. As the particles, in solid state, are closely packed, they do not have freedom for the movement. Given mass, of all pure solids have definite size, shape, volume and density. Solids are non-compressible. Solids, when heated, melt, and solid state is transformed into liquid state. In liquid state, the constituent molecules are in contact with one another. However, they are not held firmly, as in case of solid state. Hence, molecules of liquid have freedom to move from one place to another place. Liquids have definite volume, but do not have definite shape. It assumes the shape of the container in which they are stored. Liquids are very slightly compressible. The three states of matter. Liquids, when heated, boil, and transform. The three states.
Measurement of properties. Many properties of matter are quantitative in nature. When properties of matter and their measurement. Different kinds of matter have characteristic properties, which can be classified into two categories as physical properties and chemical properties. Physical properties are those which can be measured or observed without changing the chemical composition of the substance. Color, odor, melting point, boiling point, density, etc. are physical properties. Chemical properties are the properties where substances undergo a chemical change and thereby exhibit change in chemical composition. For example, coal burns in air to produce carbon dioxide, or magnesium wire burns in air in the presence of oxygen to form magnesium oxide. Measurement of properties. Many properties of matter are quantitative in nature. When you measure something, you are comparing it with some standard. The standard quantity is reproducible and unchanging. Many properties of matter. SI units. In measurement of properties. Many properties of matter are SI units. In 1960, the General Conference of Weights and Measure proposed revised metric system called International System of Units, that is, SI units. The metric system, which originated in France in late 18th century, was more convenient as it was based on the decimal system. Later, based on a common standard system, the International System of Units, SI units, was established. The SI system has 7 base units as listed in this table. These are fundamental scientific quantities. Other units like speed, volume, density, etc. can be derived from these quantities. Fundamental units: base physical quantity, length, symbol for quantity L, name of SI unit meter, symbol for SI unit M. Base physical quantity mass, symbol for quantity M, name of SI unit kilogram. Symbol for SI unit kg. Base physical quantity time, symbol for quantity T, name of SI unit second, symbol for SI unit S. Base physical quantity electric current, symbol for quantity I, name of SI unit ampere, symbol for SI unit A. Base physical quantity thermodynamic temperature, symbol for quantity T, name of SI unit Kelvin, symbol for SI unit K. Base physical quantity amount of substance, symbol for quantity N, name of SI unit mole, symbol for SI unit MOL, mole. Base physical quantity luminous intensity, symbol for quantity IV, name of SI unit candela, symbol for SI unit CD. SI units. In 1960, the General Conference of Weights and Measures SI units. Physical properties. 1. Mass and weight. We know that matter has mass, so mass is an inherent property of matter. It is the measure of the quantity of matter a body contains. The mass of a body does not vary as its position changes. On the other hand, the weight of a body is result of the mass and gravitational attraction. The weight of a body varies because the gravitational attraction of the earth for a body varies with the distance from the center of the earth. Hence, the mass of a body is more fundamental property than its weight. The basic unit of mass in the SI system is the kilogram as given in table 1. However, a fractional quantity gram is used for weighing small quantities of chemicals in the laboratories. Therefore, in terms of grams it is defined 1 kilogram is equal to 1000 gram is equal to 10 raised to 3 grams. Two, length. In chemistry, we come across length while expressed in properties such as the atomic radius, bond length, wavelength of electromagnetic radiation, and so on. These quantities are very small, therefore, fractional units of the SI unit of length are used for5. Temperature. Temperature is a measure of the hotness or coldness of an object. There are 3 common scales to measure temperature, namely degree Celsius, degree Fahrenheit, and K Kelvin. Here K is the SI unit. This figure shows the thermometers based on these scales. Generally, the thermometer with Celsius scale are calibrated from 0 degree centigrade to 100 degree centigrade, where these two temperatures are respectively the freezing point and the boiling point of water at atmospheric pressure. These are represented on Fahrenheit scale as 32 degree Fahrenheit to 212 degree Fahrenheit. The temperatures on two scales are related to each other by the following relationship. Degree Fahrenheit is equal to 9/5 degree centigrade plus 32. The Kelvin scale is related to Celsius scale as follows. K is equal to degree centigrade plus 273.15.
Laws of chemical combination. The elements combine with each other and form compounds. This process is governed by 5 basic laws. Law of conservation of mass. The law states that the mass is neither created nor destroyed during chemical combination of matter. The law was first stated by Russian scientist Lomonosov in the year 1765. Later in 1783, French scientist Antoine Lavoisier also stated the same law independently. Lavoisier studied several combustion reactions. He determined masses of the reactants accurately before reactions and after the reaction. He also determined the masses of the products. He found that the masses of the reactants before reaction were in agreement with the total masses of products after completion of reaction. Consider burning of carbon. Carbon plus oxygen gives 2 carbon dioxide. According to law of conservation of mass, the sum of masses of carbon and oxygen, that is sum of masses of the reactants, is always equal to mass of product, carbon dioxide formed during the reaction. Law of definite composition. The law was stated by French chemist Joseph Proust. The law states that any pure compound always contain the same elements in a definite proportion, by weight irrespective of its source or method of a preparation. The law is also called law of definite proportions. In support of the law, it was experimentally proved that a naturally occurring pure sample of copper carbonate contains 51.35% copper by weight, 38.91% carbon by weight, and 9.74% oxygen by weight. Further, a pure sample of copper carbonate was synthesized in laboratory, and it was found that the percentage by weight of copper, carbon, and oxygen were exactly identical to that of sample of naturally occurring sample of copper carbonate. The law was further supported by different samples of pure water. It was observed that irrespective of sources of water, it contained 88.81% oxygen by weight, and 11.19% hydrogen by weight. The different pure samples of sugar obtained 51.4% oxygen, 42.1% carbon, and 6.5% hydrogen by weight. French scientist Berthollet opposed the Proust's law of definite proportion by giving examples of the substances containing different proportions of elements. However, Berthollet's objections were ruled out, as the experimental work of analysis mentioned by Berthollet was found to be based on impure samples or incomplete reactions. Law of multiple proportions. The law was proposed by British scientist John Dalton in 1803. The law states that, if two elements chemically combine with each other, forming two or more compounds with different compositions by weight, then the masses of two interacting elements in the two compounds are in the ratios of small whole numbers. For example, carbon reacts chemically with oxygen forming two compounds, carbon monoxide and carbon dioxide. Carbon monoxide is poisonous combustible gas, while carbon dioxide is non-poisonous, non-combustible gas. On analysis, it was found that 1 gram of carbon reacts with 1.33 grams of oxygen to form carbon monoxide, and 1 gram of carbon reacts with 2.66 grams of oxygen to yield carbon dioxide. Hence, the ratios of weights of oxygen to that of carbon for two compounds are: for carbon dioxide is equal to 2.66 grams of oxygen upon 1.00 grams of carbon is equal to 2.66. For carbon monoxide is equal to 1.33 grams of oxygen upon 1.00 grams of carbon is equal to 1.33. The two ratio are in the proportion 2.66 upon 1.33 is equal to 2:1. Therefore, the ratio of masses of oxygen that combine with the same mass of carbon is 2:1. That is a simple ratio. Hydrogen interacts with oxygen to form two compounds, water and hydrogen peroxide. On analysis, it is found that water contains 88.89% by weight of oxygen and 11.11% by weight of hydrogen. Therefore, the ratio of percentage by weight of oxygen to that of hydrogen is equal to 88.89% by weight of oxygen upon 11.11% by weight of hydrogen is equal to 8:1. Similarly, hydrogen peroxide contains 94.12% by weight of oxygen and 5.88% by weight of hydrogen. Hence, the ratio of percentages by weights is equal to 94.12% by weight of oxygen upon 5.88% by weight of hydrogen is equal to 16. Is equal to 16:1. Finally, the two ratios of the two compounds are in the proportion 16:1 upon 8:1 is equal to 2:1. Therefore, the ratio of weights of oxygen that combine with same weight of hydrogen is equal to 2:1. Gay-Lussac's law of combining volumes of gases. French chemist Joseph Louis Gay-Lussac studied number of gaseous reactions and discovered that there is a definite relationship between volumes of gaseous reactants and that of gaseous products. He generalized his observations and stated Gay-Lussac's law of combining volume as: when gases react together to produce gaseous products, the volumes of reactants and products bear a simple whole number ratio with each other, provided volumes are measured at same temperature and pressure. Illustrations. 1. Under identical conditions of temperature and pressure equal volumes, say 1 liter. That is 1 liter of each hydrogen and chlorine gases react together to produce double the volume, 2 liters of hydrogen chloride gas. That is, hydrogen plus chlorine gives 2 hydrogen chloride. 1 liter plus 1 liter gives 2 liters. 1 volume plus 1 volume, gives to 2 volume. Thus, the ratio of volumes is 1:1:2. 2. Under identical conditions of temperature and pressure, 2 liters of hydrogen gas react with 1 liter of oxygen gas to produce 2 liters of steam, water vapor, that is, hydrogen plus oxygen, gives to steam water vapor. 2 liters plus 1 liter gives to 2 liters. 2 volume plus 1 volume gives to 2 volume. The ratio of volumes is 2:1. To 2. 3. Under identical conditions of temperature and pressure, 1 liter of nitrogen gas reacts with 3 liters of hydrogen to produce 2 liters of ammonia gas, that is, nitrogen plus hydrogen, gives to ammonia. 1 liter plus 3 liters gives to 2 liters. 1 volume plus 3 volume, 2 volume. Here, the ratio of volumes is 1:3:2. All examples cited above indicate that, during gaseous reactions, gaseous reactants and products bear a simple ratio of whole numbers of volumes with each other. Volumes may be measured in any convenient unit like liter, milliliters, centimeter cube, decimeter cube, etc. For example, consider the reaction. Sulfur dioxide plus oxygen gives to sulfur trioxide. 200 milliliters plus 100 milliliters gives to 200 milliliters. 1 volume plus 1/2 volume gives to 1 volume. So that, the ratio of volumes is 2:1:2. Note that, the volumes are not additive. Though, in case of reaction between hydrogen and chlorine gases, it appears that volumes are additive. However, in case of hydrogen-oxygen reaction, 2 volumes of hydrogen and 1 volume of oxygen, equal to 3 volumes of reactants, get converted into 2 volumes of product steam. Similarly, in case of formation of ammonia, 1 volume of nitrogen reacts with 3 volumes of hydrogen, equal to 4 volumes of reactants, get converted into 2 volumes of product ammonia. Avogadro's law. Gay-Lussac's law of combining volumes of gases was stated in 1808. Simultaneously, in the same year, Dalton proposed atomic theory. Avogadro, in year 1811, combined Gay-Lussac's law and Dalton's theory to propose Avogadro's law. It states that equal volumes of all gases, under identical conditions of temperature and pressure, contain equal number of molecules. Avogadro introduced the idea of molecule as the smallest particle of a compound. Dalton believed that compounds are formed when atoms of different elements combine in a fixed ratio. It was firmly believed that the atoms of the same element do not combine to form a molecule. Avogadro suggested that most of the gases do not exist in the atomic state, but exist as polyatomic molecules. Like diatomic hydrogen, H2, diatomic oxygen O2, nitrogen N2 or chlorine Cl2, etc. These diatomic molecules take part in the reaction, as atoms do not exist in free state. That was the most revolutionary idea. Avogadro's hypothesis was published in French journal, Journal de Physique in 1811. The idea suggested by Avogadro was totally neglected by scientist community for over 50 years. The idea of existence of a pure element, as diatomic molecule, was difficult to digest. Finally, in 1860, in the first International Conference on Chemistry, held in Germany, Stanislaw Cannizzaro explained the importance of Avogadro's hypothesis. And only then the precious work was recognized. Mathematically, Avogadro's law is stated as, at constant pressure and temperature, volume of a gas is directly proportional to the number of molecules. V is directly proportional to the number of molecules, where pressure and temperature constant. But number of molecules is directly proportional to the n, the number of moles of gas. Hence, V is directly proportional to n, or V upon n equals constant, where number of moles, n, equals mass of gas, upon molar mass of gas. At STP, it may be possible to calculate volume per mole, V upon n, of an ideal gas. According to general gas equation, PV equals nRT. Hence, at STP, V upon n equals RT upon P, where R equals moles 0.08205 liter atmosphere, per moles, per Kelvin. V upon n equals 0.08205 a liter atmosphere per moles per Kelvin into 273.15 Kelvin upon 1 atmosphere equals 22.4141 liter per moles. Hence, the volume of 1 mole of any pure gas at standard temperature and pressure is always constant equal to 22.414 liters or 0.022414 cubic meters. This value is called as Avogadro's molar volume, or molar gas volume at STP. Dalton's atomic theory. Greek philosopher Democritus, in the year 460 to 370 BC, suggested that matter is composed of extremely small, atomio, mean indivisible particles. The tiny, small, indivisible particles of matter were called atoms. In the year 1808, when different laws of chemical combinations were stated, John Dalton, English school teacher, proposed atomic theory. In his theory, made following assumptions. 1. All matters are made up of tiny, indestructible, indivisible unit particles, called atoms. Atoms are the smallest particles of the element, and molecules are the smallest particles of a compound. 2. All atoms of the same element have same size, shape, and mass, and all other properties. Atoms of different elements have different properties. 3. Compounds are formed when atoms of different elements combine. The atoms in a compound unite in small whole number ratios, like 1:1, 1:2, 1:3, 2:1, 2:3, etc. 4. A chemical reaction involves only the separation, combination, or rearrangement of integer number of atoms. During chemical reaction, atoms are neither created nor destroyed. With these assumptions, Dalton explained law of conservation of mass. He stated that, during chemical reaction, atoms can rearrange and change their partners. Molecules could be decomposed into atoms. But the total number of atoms in the reactants and products must be same. Hence, mass is conserved during a reaction. Law of multiple proportions was explained by Dalton by assuming that, under some conditions, atoms of two types combine in the ratio 1:1 to form a molecule. Under some different conditions, it may combine in the ratio 1:2, or 1:3, or 2:3, etc. Dalton also proposed some symbols for some common atoms and molecules, shown in the above figure. Oxygen, sulfur, nitrogen, hydrogen, carbon, potassium, water, methane, carbon monoxide, hydrogen peroxide, carbon dioxide. Atomic and molecular masses. Every atom of an element consists of fixed number of protons, neutrons, and electrons, the subatomic particles. The number of protons varies from atom to atom. The mass of the atom changes as the number of subatomic particles is changed. Hence, masses of different atoms, of different elements, are different. The size of single atom is of the order of 10 raised to minus 15 meter. And the mass is of the order of 10 raised to minus 27 kilograms. Hence, it is not possible to weigh a single atom. However, it is possible to determine masses of the atoms of the elements relative to mass of some standard element experimentally, using mass spectrograph. The standard element chosen is assigned appropriate value of mass of atom. By international agreement, in 1961, for determining atomic masses, carbon-12, a distinct atom of carbon was chosen as standard with its atomic mass. 12, atomic mass unit, abbreviated as AMU, and defined as 1 upon 12 of the mass of an atom of carbon-12, equal to 1.6605 multiplied by 19 raised to minus 24 gram. The masses of all other atoms are determined relative to the mass of an atom of carbon-12, the standard. Recently, the unit of atomic mass, AMU, is replaced by U, meaning unified mass. Using mass spectrograph, atomic masses of different elements were determined. It was found that atomic mass of hydrogen is 1.008 U. That of carbon, 12.011 U. And that of iron is 55.85 U. Careful investigation of mass spectrograph shows that natural hydrogen contains 3 isotopes of hydrogen in a definite proportion, so that the observed atomic mass 1.008 U. Similarly, carbon contains 3 isotopes C12, C13, and C14, so that the observed atomic mass is 12.011 U.
Problem 1.1. Mass of an atom of oxygen in gram is 26.56896 into 10 raised to minus 24 gram. What is the atomic mass of oxygen in Dalton? Solution. Mass of an atom of oxygen in gram is 26.56896 into 10 raised to minus 24 gram and 1.66056 into 10 raised to minus 24 gram is equal to 1 Dalton. Therefore, 26.56896 into 10 raised to minus 24 grams is equal to what? Is equal to 26.56896 into 10 raised to minus 24 gram upon 1.66056 into 10 raised to minus 24 gram per Dalton, which equals 16 Dalton. Similarly, mass of an atom of hydrogen is equal to 1.0080 Dalton.
Average atomic mass. Isotopes are the atoms of the same elements, having same atomic number, containing same number of protons and electrons, but different number of neutrons. Hence possess different mass numbers. Many naturally occurring elements exist, in the form of two or more isotopes. The observed atomic mass of the atom of the element is the average atomic mass of the elements, taking into consideration the natural abundances of the isotopes. The natural abundance means percentage occurrence. The mass spectrometer, with higher precision, shows variation of exact atomic mass of the isotope of the elements, with its relative abundance. With the help of Aston's mass spectrometer, it was proved that neon exists in nature in the form of mixture of three isotopes. 1. Neon 20, with atomic mass 19.9924 U, with natural abundance 90.92%. And 2. Neon 22, with atomic mass 21.9914 U, with natural abundance 8.82%. 3. Neon 21 with atomic mass 20.9940 U, with natural abundance 0.26%. From this data, it is possible to calculate observed atomic mass of neon in terms of average atomic mass. Average atomic mass of Ne is equal to atomic mass of Ne20 multiply by percent of Ne20 plus atomic mass of Ne22 multiply by percent of Ne22 plus atomic mass of Ne21 multiply by percent of Ne21 upon 100 is equal to 19.9924 U multiplied by 90.92 plus 21.9914 U multiply by 8.82 plus 20.994 U multiplied by 0.26 upon 100 is equal to 20.1707 U. Problem 1.1. Lithium exists in nature in the form of two isotopes, Li6 and Li7, with atomic masses 6.0151 U and 7.0160 U, and the percentages 8.24 and 91.76 respectively. Calculate average atomic mass. Solution. Average atomic mass of Li is equal to atomic mass of Li6 multiply by percentage plus atomic mass of Li7 multiply by percentage upon 100 is equal to 6.0151 U multiplied by 8.24 plus 7.0160 U multiplied by 91.76 upon 100 is equal to 6.934 U. Problem 1.2. Chlorine. Average 4.40%. Molecular mass. Molecule of a substance is also very small, like an atom. And its mass is also small, of the order of 10 raised to minus 26 kilograms, which is not convenient to use. The molecular mass is also expressed as a relative mass, compared to mass of standard atom of carbon-12. Molecular mass of a substance is defined as the ratio of mass of one molecule of a substance to 1/12 of mass of one atom of carbon-12. It is also the algebraic sum of atomic masses of constituent atoms, which constitute the molecule. Molecular mass is also expressed in AMU. It is a number that indicates comparative mass of a molecule of a compound, with respect to 1/12 of the mass of one atom of carbon-12. Molar mass is the molar mass expressed in gram. 1 gram molar mass, also called 1 grand molecule, or 1 gram mole, or simply 1 mole. 1 mole of the element means amount of the element equal to its atomic mass in gram, and also called 1 gram atom of the element, or 1 mole of the element.
Problem 1.3. Find the mass.
Formula mass. Some substances such as sodium chloride do not contain discrete molecules as the constituent units. In such compounds, cationic, sodium, and anionic chloride entities are arranged in a three-dimensional structure. In sodium chloride crystal, one sodium ion is surrounded by 6 chloride ions, all at the same distance from it and vice versa. Therefore, NaCl is just the formula used to represent sodium chloride, though it is not a molecule. Similarly, a term formula mass is used for such ionic compounds instead of molecular mass. The formula mass of a substance is the sum of atomic masses of the atoms present in the formula.
Mole concept and Avogadro number. The mass of a single atom, of an element, or single molecule of a compound, is negligibly small, and it is difficult to weigh. The quantity of a substance, equal to its atomic mass, or molar mass in gram, is referred as 1 mole of the substance. 1 mole of the substance is defined as the amount of substance that contains the number of particles, atoms, molecules, ions, or electrons etc. as present in 0.012 kilograms of carbon-12. This number of particles is determined to be equal to 6.022 into 10 raised to 23 particles. The number 6.022 into 10 raised to 23 per moles is called Avogadro number N. A. This is the number of atoms, molecules, ions, electrons present in 1 mole of a substance. This number of electrons makes an electrical charge of 1 Faraday. 1 mole of different gases, having different molar masses occupy same volume, of 22.414 liters, and contain 6.022 into 10 raised to 23 molecules, is illustrated, as shown in the above figure. The relationship between mass of gas, with number of moles, volume of gas, at STP, and the number of molecules, are given by mole triangle, as shown in the above figure. Following relationships are important while attempting numerical. 1. Number of moles. N equals mass of the substance, upon molar mass of the substance. 2. Number of molecules, equals, N into Avogadro number. 3. Volume of gas, at STP, equals, N into 22.414 liters.
Molar mass. The mass of 1 mole of a substance, element, compound in grams is called its molar mass. The molar mass of any element in grams is numerically equal to atomic mass of that element in U. Element H, atomic mass U, 1 U. Molar mass G per mole, 1 G per mole. Element C, atomic mass U, 12 U. Molar mass 12 G per mole. Element O, atomic mass U, 16 U. Molar mass 16 G per mole. Similarly, molar mass of any substance existing as polyatomic molecule in grams is numerically equal to its molecular mass or formula mass in U. Polyatomic substance O2, molecular formula mass U, 32 U. Molar mass G per mole, 32 G per mole. Polyatomic substance H2O, molecular formula mass U, 18 U. Molar mass 18 G per mole. Polyatomic substance NaCl, molecular formula mass U, 58.5 U. Molar mass 58.5 G per mole. Molar mass of O atoms is equal to 6.022 multiplied by 10 raised to 23 atom per mole multiplied by 16 U per atom multiplied by 1.66056 multiplied by 10 raised to minus 24 G upon U, which is equal to 16 G per mole.
Problem 1.5. Problem 1.5.